So let us look at the following example that will deal with an adiabatic and slow expansion of an ideal gas. So let's begin. A certain diatomic ideal gas is expanded adiabatically and slowly. Initially, 1 mole of ideal gas is at a pressure of 101,300 newtons per meter squared and a temperature of 25 degrees Celsius. The final volume increases by a factor of 1.8. Calculate the final pressure of our ideal gas. So in step 1, we essentially have to realize what equation we have to use. So because we're dealing with a slow and adiabatic expansion of an ideal gas, and because we want to calculate the final pressure, we could use the following equation. The product of the pressure and the volume, where the volume is raised to the power of Cp divided by Cv, is always equal to the same constant. Now, Cp is the molar specific heat when the pressure is constant, and Cv is the molar specific heat of our ideal gas when the volume is constant. So before we could actually use this equation, we have to determine what the ratio Cp to Cv is. So let's move on to step 2. In step 2, that's exactly what we will do. So by the equal partition principle of energy, we know that Cv, the molar specific heat when the volume is constant, is equal to 5 divided by 2 multiplied by R, the universal gas constant. Now, from the lecture on molar specific heat, we saw that the relationship between Cp and Cv and R was given by the following equation. So Cp is equal to the sum of R and Cv. So now let's actually determine what this ratio is. So we want to find what Cp divided by Cv is. So Cp divided by Cv is equal to, where Cp is equal to Cv plus R. That's exactly what we write here. So Cv plus R divided by Cv. Now, from the equal partition principle of energy, we know that Cv is equal to 5 divided by 2 multiplied by R. So we substitute that into Cv. So we have 5 divided by 2 multiplied by R plus R divided by 5 divided by 2 multiplied by R. Now, this R is the same thing as 2 divided by 2 multiplied by R. So the top becomes 7 divided by 2 multiplied by R, and the bottom remains at 5 divided by 2 times R. The R's will cancel, the 2's will cancel, and we're left with 7 divided by 5. So, notice the reason that Cv is equal to 5 divided by 2 times R and not 3 divided by 2 multiplied by R is because we're dealing with a diatomic ideal gas and not a monatomic ideal gas. So Cv is equal to 5 divided by 2 multiplied by R. So the ratio Cp divided by Cv for a diatomic ideal gas is equal to 7 divided by 5. So now we're ready to use this equation to solve for our final pressure. So the initial pressure P1 multiplied by the initial volume V1 raised to the power of 7 divided by 5 is equal to the final pressure P2 multiplied by the final velocity V2 raised to the power of 7 divided by 5. So we want to solve for P2. So let's bring this to the left side. We see that P2, the final pressure, is equal to the product of P1 multiplied by V1 divided by V2 raised to the power of 7 divided by 5. Now we know that the final volume increases by a factor of 1.8. So V1 divided by V2 is 1 divided by 1.8. And we know P1 is simply 101,700 newtons per meter squared. So we see that P2 is equal to this multiplied by the ratio of 1 divided by 1.8 raised to the power of 7 divided by 5. And that gives us approximately 44,486 newtons per meter squared is the final pressure in our adiabatic and slow expansion of a diatomic ideal gas.